Vector databases sound complicated, but their core job is actually very simple: retrieving information based on meaning instead of exact wording. Because language is messy. People phrase the same idea very differently. Documents use different terminology, but the meaning stays similar while the wording changes. And traditional retrieval systems struggle with that. That's the problem that vector databases were built to solve. In this video, we'll break this into three parts: the retrieval problem, how vector search actually works, and where these systems still start to break down. Welcome to Schovia, where we make AI concepts feel like everyday ideas. Let's start with a normal database. Let's say you run an online store. You have customer tables, like order tables, shipping records, etc. If you want to retrieve customer 1842, SQL databases are excellent at that. Exact lookup is easy. Even filtering is easy. Finding all customers from California or finding all the purchases that are above $100 or finding all orders from last month. Traditional databases were designed for this type of structured information. But now imagine a different kind of query. The user asks, what happens if my package arrives damaged? Your support documentation might never use those exact words. Maybe the actual article says how to request replacement for items damaged during shipping. Semantically, those are almost identical, but lexically, they are completely different. And this is where traditional retrieval starts struggling, because keyword search mostly looks for overlapping words. But humans rarely phrase things consistently. Different teams will write differently, different users will ask the same question in a different way, and the documents may use a different terminology. So the problem is no longer exact matching, it's about semantic retrieval. For information with similar meaning, even when the wording changes entirely. That's the core problem vector databases help solve. So if keyword retrieval breaks, how does the system retrieve based on meaning instead? The answer starts with embeddings. An embedding is just a numerical representation of the meaning. The model takes text and converts it into a vector, which is a long list of numbers. Those numbers themselves are not important. What matters is their position in the multidimensional space. Similar meanings end up close together in this high dimensional space. Different meanings end up further apart. So, for example, dog bites man and man attacked by dog would likely produce embeddings that are very close, while something like quantum field theory lecture would land somewhere completely different. The model has effectively transformed language into geometry. And that's the key intuition. Meaning becomes spatial proximity. But now the system needs a way to measure proximity. How do you decide whether two vectors are close? Usually the system computes some form of vector similarity, and the most commonly used ones are cosine similarity, dot product, or Euclidean distance. The exact math isn't the important part here. The important idea is that vectors pointing in similar directions tend to represent similar meanings. So retrieval becomes a ranking problem. The system compares the query vector against stored vectors and retrieves the closest matches. And once meaning becomes geometry, retrieval becomes a nearest neighbor search problem. So instead of asking which documents contain these exact words like the traditional databases, the system now asks which vectors are closest to this query vector. That's vector search. Now, this is where the vector database enters the picture. The database usually stores three things: the embedding vector, the original text chunk, and metadata. Metadata could include things like document IDs, timestamps, permissions, source information, or filtering rules. The vector database itself is not generating intelligence. It's organizing embeddings so that similarity search can happen efficiently at scale. Because brute force comparison is very expensive. If every query had to compare against millions of stored vectors one by one, retrieval would become far too slow. So, vector databases use specialized indexing techniques for approximate nearest neighbor search known as ANN search. The important word there is approximate, which helps with fast retrieval instead of a perfect one. Now let's connect this to RAG systems, retrieval augmented generation. Here's the simplified pipeline. First, the documents get split into chunks. Those chunks are converted into embeddings. Those embeddings are stored in a vector database, and when a user asks a question, the question also gets converted into an embedding. The system searches for nearby vectors, like the most relevant chunks, and they get retrieved. And then those chunks are inserted into the LLM's context window before the LLM can respond to the user's question. That's the retrieval loop. The language model itself is not searching the database directly. The retrieval system prepares the context first. So you can think about it as sophisticated prompt engineering where you provide the right context. This is why RAG systems can answer questions about information the LLM model was never originally trained on. But this is where the simplified explanation usually stops because retrieving similar information turns out to be much harder than people expect. Take chunking, for example. Imagine embedding an entire 40-page PDF as a single vector. Now, a user asks about one refund policy which is buried in page 32. That embedding contains too many mixed concepts. The retrieval signal becomes weak, and the system, when it splits documents into smaller chunks, those chunks again may create another problem on top of it. You gain precision, but you lose the global context. Now, the model may retrieve isolated fragments that lack the surrounding information. So, this becomes a balancing problem of chunk size, overlap strategy, semantic boundaries, and metadata filtering. All of these affect retrieval quality before the vector database even gets involved. And there's another subtle issue. Similarity is not the same thing as understanding. Two pieces of text can look semantically close in embedding space while still being operationally wrong. Imagine a medical system retrieval, and the query about pediatric dosage retrieves an adult dosage guideline because the wording looks highly similar. The embeddings may be close, but the consequence is completely different. This is why production systems rarely rely on vector search alone. They often combine vector retrieval with keyword search, re-ranking models, metadata filters, and domain constraints. Because semantic similarity is useful, but perhaps not by itself, relevance control still matters, especially in high-stakes systems. And this is also why retrieval quality matters so much in RAG. Bad retrieval produces bad context. Bad context produces hallucinations, irrelevant answers, or misleading outcomes. In many real world systems, retrieval quality matters just as much as model quality, sometimes more. At a high level, vector databases are solving a very specific problem. How do you retrieve information based on meaning instead of exact wording? And that's the core idea. The embeddings convert language into geometry, and vector databases make similarity search efficient. And systems like RAG use retrieval to supply external context before generation begins. The real complexity of the pipeline isn't just storing vectors. It's the design of these retrieval systems that consistently return the right context for the decision the model is about to make. And that's where chunking matters, ranking matters, filtering matters, and the system design matters. Because in production AI systems, retrieval is a part of the reasoning pipeline itself. If you found this useful, please subscribe to Schovia, and as always, stay curious.